Hi, and welcome to my presentation on Omni. We present a method for volumetric sensing and actuation of passive magnets, especially for haptic feedback system. This work was done in collaboration with Juan and other colleagues at ETH Zurich. Virtual and augmented reality are gaining more and more momentum. This is mainly due to the promise for immersive experiences. Current systems are mostly focused on rich visuals to cater towards the end user. However, to increase the immersion into a carefully crafted, artificial world, it is necessary to also support the sense of touch and to provide tactile feedback when interacting with virtual objects in 3D. A lot of prior work exists on this, ranging from mechanical contraptions to vibro tactile stimuli. Also larger electromagnetic surfaces have been explored. Especially relevant is normal touch by Benko and colleagues. They propose actuated handheld controllers that render the shape of virtual objects through physical shape displacement, thereby enabling users to feel 3D textures, surfaces and forces that match the visual rendering. Also relevant is butterfly haptics of Berkman and colleagues. The large problem with both of these systems is that they require external tracking or are cumbersome. In the end, the goal of the user is to have an affordable system to deliver significant untethered forces in a closed-loop fashion. A keyword here is affordable. One way to achieve this, for instance, is to make the system self-contained. Secondly, untethered, air-gapped and free of mechanical contraptions. A common solution for this is the use of electromagnetism. Finally, the system should act on the user. This means that it should be able to sense inputs. All this gives rise to the question on how we can leverage electromagnetism for actuation as well as sensing. To this end, we have three contributions in our paper. A hardware contribution, we suggest a method of position reconstruction, and we actuate at the same time. Let's first discuss the hardware. In terms of actuator, there is some related work. First of all, there is the work of Petruska. They propose an electromagnet with 3 orthogonal coils. Their square design, however, does not create a homogeneous magnetic field, providing different perceived forces at the same distance. Secondly, there is the work of Zarate and colleagues. They have a spherical electromagnet. However, the coils are not intertwined. This results in less force and more heating compared to our design. Furthermore, they require external tracking. In our system, a permanent magnet is embedded inside the tool. The actuator, a spherical electromagnet, consists out of an iron core and 3 intertwined copper coils. Below that, there is a PCB. On the PCB are 8 3D Hall sensors that enable tracking of the tool. Finally, the whole system is cooled by a fan. Now that we have an overview of the hardware, let's dive right into the details on tracking. Tracking permanent and electromagnets has been a popular topic. Taylor and colleagues tracking multiple magnets with analytical calculated gradients. Chen and colleagues can track multiple fingers and identify them by attaching electromagnets to them. Our approach differs in the sense that we have an actuator in the same modality, electromagnetism, thereby adding extreme noise to the tracking signal. To understand our method, let's start from the beginning. The first step is to measure a Hall sensor. This provides you with a magnetic field at a certain location. In this case, it mainly consists out of noise made by the Earth's magnetic field. This magnetic field is influenced by a permanent magnet in a tool. However, it is possible to approximate this influence with a theoretical model, the so-called dipole-dipole model. This is denoted in blue, and that is step 2. Step 3 is to use a similar model on the spherical electromagnet. So now our Hall sensor measures the tool, the actuator and the noise. Magnetic fields form a superposition and therefore can simply be summed. So the real-world measurements are approximated by the sum of our models as well as the noise. For the exact models, please refer to the paper. We can move over the measured field to the right-hand side of this equation. If our models are perfect, this cost should approach 0. We can change our model by moving the permanent magnet around, position P. So our tool is likely located where this cost is minimum. We can do this by taking the gradient of the cost with regard to the position. Then we do simple gradient descent till our cost and gradient approach 0. For a more detailed algorithm, please refer to the paper. However, we specifically use a quasi-Newton method, which is strong for non-linear problems. Here you can see the tracking as observed through a mixed reality headset. Since the method uses gradient descent under real-time optimization, it takes approximately 50 milliseconds to converge. We now have an actuator that can track our tool, but how do we actually provide forces? For this, we can forget about the Hall sensors. We just have a tool with a permanent magnet and a spherical electromagnet. The force in 3 directions can be changed by altering the current. The permanent magnet in the tool is assumed to always point towards the sphere, so that the same pole of the magnet always points towards the center. Let's now take a closer look at the forces themselves. We can not only apply attractive forces by having the different poles. By rotating the magnetic field of the spherical electromagnet, we can also repel the tool. Or we can even create tangential forces, where the user perceives a sideward force. And the forces can be combined, so that the user perceives a combination of forces. More details on how to calculate the input based on the desired forces are proposed in our paper. During experiments, we have measured forces up to 2 newtons for 30 seconds. Lower forces can be sustained indefinitely. This is enough to lift an apple. Furthermore, we show that we can rotate the magnetic field, here with ferromagnetic fluid, but also with a permanent magnet, in this case one that is also found in our tool. Let's take a look at how accurate we can track. For this, we use the 10-camera OptiTrack. We measure the tracking with and without actuating. Here we see a violin plot that plots the distribution of errors. We can see that our tracking without actuation is around the 5 mm Euclidean distance. With actuating, this moves up to a bit less than 7 mm. However, in both cases, the error per axis stays well below 5 mm. Now that we have an idea on how accurate we can track, let's see what applications our system enables. One of the applications we propose is for designers. Here, a person is extruding from a shape. While extruding, the person perceives attractive forces. Another option is to explore non-rigid bodies. Here, a person is bravely poking a dragon. Upon impact, the user perceives a force away from the dragon. Finally, our system can be used for gaming, here in a joystick-like fashion. Upon impact on the wall, the user perceives a large attractive force. there is a future work ahead of us. One of the things is that we need to improve the tracking. This can for instance be done by improving the model we have of our world. Our method can also be extended to track multiple tools. This could potentially open up more use cases. And finally, we need to evaluate the whole system with users. To summarize, in this paper we introduced new hardware that is capable of tracking and actuation. We introduced a method for position reconstruction and showed how this can be used during actuation. All blueprints and codes are available on our webpage. Thank you.